All right, welcome. In this video, we're going to talk through our balancing and stoichiometry review problems here. So first, let's take a look at balancing chemical equations. So one of our goals is to be able to use coefficients to balance chemical equations. So a reminder of vocabulary here, if you see something like this, 2NH3, the big number out in front is called the coefficient. And then this small number down here, this is the subscript. And the way that these work, the subscript just applies to the number right in front of this. So this means you've got like 3 hydrogens, but it does not apply to the nitrogen. So you've got 3 hydrogens and only 1 nitrogen here. And then the coefficient tells you how many of this whole molecule you have. So if I were to draw this out, if you're a visual person, you might find it useful to draw this out. So 2 NH3s looks like this. So notice when I have 2 NH3s, I have 2 nitrogen atoms, and then 1, 2, 3, 4, 5, 6 hydrogen atoms. Okay, so that's just a little background about coefficients and subscripts. So now let's go over and balance some equations. So my process for balancing equations is I make a little T-chart, and I'm going to look at what elements are involved in my reaction. So this reaction involves silver and sulfur. Okay. And over on the left, if I see no coefficients, no subscripts, that just means there's just one of that atom. So sulfur and silver are both just one. And then over here on the right, notice how I have a subscript over there. So that tells me that there are 2 silver atoms on the right. And then sulfur does not have a subscript, so it's just 1. So it looks like my equation right now is not balanced. And that's because we have a different number of atoms on the left and the right. So on the left, I have 1 silver. On the right, I have 2 silvers. So some silvers seem to have appeared from thin air, which cannot happen. In real life, we need to follow the law of conservation of matter, which tells us atoms cannot be created or destroyed. So I want to try and balance this out, and I can balance it using coefficients. So over here on the left, I can put a coefficient here in front of my silver. Now I have 2 atoms of silver on the left, and look, everything's balanced. Hooray! So I just want to check to make sure my number of each atom is the same on the left as the right. So let's try this with another one. This one involves aluminum and oxygen. So on the left, I have 2 aluminum, so you can see that subscript there, and I have 3 oxygens. There's my subscript. On the right, there are no subscripts or coefficients for aluminum, so that means there's just 1 atom of aluminum. And then there's a subscript there, so I've got 2 atoms of oxygen on the right. And I am going to notice how these are both not balanced, the aluminum and oxygen. So I'm just going to pick one to start with. And I'm going to pick this bottom one to balance my oxygens first. So notice I have 3 oxygens on one side, 2 oxygens on the other side. I want to find a number that these could both have in common, and we call that the lowest common multiple, right? So 3 and 2, what's the lowest common multiple they have? That's 6. So I'm going to try and make it so I can have 6 atoms of oxygen on each side. So on the left, what I can do is I can put a 3 out in front of it. And what that means, I'm going to have 3 molecules of oxygen. So I'd have 1, 2, 3, 4, 5, 6. I'm going to have 6 oxygen atoms overall. So I've got 6 oxygens now on the left. So over here, I'll make it so I have 6 oxygens here. So I'm going to put a 2 out in front. That makes it so I've got 2 aluminum oxides. So I've got Al2O3, Al2O3. I've got that twice. So now I've got 6 oxygens. I also have 4 aluminums. So now my aluminums are still not balanced. So on the right, I need to also have 4 aluminums. So I can put a coefficient out front. Now I've got 4 aluminums on the right. So yay, that one is balanced. Check. Okay. Let's go on to this one. So whenever you see a reaction that involves just carbons, hydrogens, and oxygens, one of the tricks is to balance them in that order. Go your C's, H's, and O's. Do them in that order. So I'm going to count my C's. I've got 14 on the left. I've got 30 H's on the right. I got 2 O's. And over here on the right, I got 1. I've got 2, and I've got 1, 2, 3. Careful with O. It shows up in more than one spot, so it's kind of tricky. You got to add those up. All right, so there's my T-chart. And then I'm going to balance my C's first. So I'm going to put a 14 over here to give me 14 carbons. And now that's going to give me 14 times 2, so that's 28 plus 1. I have 29 oxygens on the right now. So every time I change a coefficient, I'm going to update my tally on the bottom. All right, now let's look at the hydrogen. I've got 30 on the left. I want to have 30 on the right. So if I make 15, 15 times 2 is 30. So now my hydrogen's balanced. But oh no, that now I have to update my oxygen count again. So I've got 14 times 2, so 28 plus 15. So that ends up being what, 43 oxygens. Okay. So now my carbons and my hydrogens are good. My oxygens are definitely not balanced. I have 43 on the right and only 2 on the left. So what number times 2 would give me 43? Well, 43 divided by 2 is 21.5. So if this number could be a 21.5, then I would have 43 oxygens on the left and the right, and I would be balanced. But I can't have half of an oxygen, so I can't just leave it like this as a decimal. So if you find yourself in this situation, what you're going to do is you're going to multiply everything by 2. Multiply the whole thing by 2. When you do that, then this becomes a 2. This becomes a 43. Double this, it becomes 28. Double this, it becomes 30. If we update our count down here, now we have 28 carbons on each side. We're going to have 60 hydrogens on each side. And now we've got what, 80? Ooh, we got a lot of oxygens. We got 86 oxygens on each side. And now we are balanced. All right, now let's think about like what these equations tell us. So the important thing about these balanced chemical equations is they tell us something called the mole ratio. So the coefficients in the balanced chemical equation tell us the mole ratio. So looking at this reaction that we just balanced, it tells us that for every 2 of these molecules, the C14H30, every 2 of those that react, we're going to make 28 moles of CO2. And so we call that our mole ratio. We get that from our coefficients. All right. So now let's talk about applying this to what we call a stoichiometry problem. So let's say here we've got a balanced chemical equation given already. So it tells us every 2 moles of magnesium is going to react with 1 mole of oxygen to make 2 moles of magnesium oxide. And our question is, if we have 250 grams of oxygen gas, how many grams of magnesium oxide can we make? So you want to do a calculation here, stoichiometry. So we're going to use our mole map, and we're starting over here with 250 grams of oxygen. And this mole map can help us tell us the steps we can take to get from where we're starting, which in this case is grams of oxygen, to what we want to find, which in this problem is grams of magnesium oxide. So our first step is we're going to use the molar mass to convert grams of oxygen into moles of oxygen. And the molar mass we find on the periodic table. So I'm going to look on the periodic table, and it tells me that 1 mole of oxygen, that each oxygen atom is 16. So if I have 2 oxygen atoms, that's O2, it's going to weigh 32 grams. So I'm going to use my molar mass of oxygen to convert grams into moles. My next step is I'm going to use my mole ratio we were just talking about. Remember, the coefficients tell us the mole ratio. Then we're going to use that to convert from moles of oxygen into moles of the thing I'm trying to find, which is magnesium oxide. So if I look up at my mole ratio here, in this equation, it looks like for every 1 oxygen, you get 2 magnesium oxides. So for every 1 mole of oxygen, you get 2 moles of magnesium oxide. All right, so now we're here. So now we need to just go one more step. Once I know moles magnesium oxide, I want to find grams magnesium oxide. Again, I'm going to look on the periodic table and use the molar mass. So if I look on the periodic table, I can see that 1 mole of magnesium oxide, if you add up the Mg and the O, you get 40.3 grams. So that ends up being, let's see, 629.8 if you plug that all in your calculator. And how you plug in your calculator is just the way it's written. So 250 times 1 divided by 32, times 2 divided by 1, times 40.3 divided by 1. Make sure you're practicing actually plugging these into your calculator so you understand like what this setup actually means, right? So that is my final answer. Something I want to check for is you should notice the units cancel out, like a unit, like grams O2. If it's on the top here, it should be on the bottom there. Moles O2 is on the top and the bottom. Moles MgO is on the top and the bottom. What we're left with is grams, which is what we were hoping to find. So that's a good way to check that your setup is good. So another learning target is this idea of percent yield. So we've done 2 labs with percent yield. We did the Alka-Seltzer lab and the collecting copper lab. And the percent yield is what you actually got divided by what you theoretically should have gotten. And what you actually got is you go ahead in a lab and you collect something and you weigh it. And in this case, it looks like we perform this experiment in the lab. We collect 601 grams of magnesium oxide. Your theoretical yield is the thing that you calculate. So theoretical is your calculated value. So in this case, it's 629.8. That's what we calculated that we should have gotten. So if you plug this in your calculator, you get about 95% yield, which is actually pretty darn good for an experiment. You'd be pretty happy with that. Okay, so one more balancing. Yeah, let's take a look at this one because there's another trick we can think about with balancing. Remember that if you see like a polyatomic ion, it can make your life a lot easier if instead of breaking like the NO3 down into N's and O's and counting those separately, we can just treat it as just one object. So I'm going to count the number of NO3s. I'm going to do the same thing with my phosphates, PO4. So what I'm going to do is I'm going to say on the left-hand side, I got 1 magnesium, and then I've got 2 NO3s. I've got 2 of whatever is inside that parentheses. And then I've got 1 aluminum, and I've got 1 PO4. And over on the right, I've got 1 aluminum, I've got 3 nitrates, I've got 3 magnesiums, and then I've got 2 PO4s. So the way parentheses work is that number tells you how many there are of the things inside the parentheses. Okay, so I'm going to pick something to balance. I'm going to go with the magnesium first, because that looks easy to balance. So I'm going to put a 3 over here. That'll balance my magnesiums. But now it'll make it so I've got 3 times 2. I'm going to have 6 nitrates. All right, I'm going to do the phosphates next, PO4. I want to have 2 PO4s over here, so I'm going to put a 2 out here. That's going to give me 2 PO4s. It also will change my aluminums. So whenever you change coefficient, update your count down here. Let's see, and the only thing that is not balanced looks like is my aluminum here. And put 2. That will give me 2 aluminums, and now I've got 2 times 3. I've got 6 nitrates. So hooray! It looks like I am all balanced. Boom. Okay, so now using that balanced chemical equation, let's do one more stoic problem. And we've got, the question is, in order to, let's see, if you react 112 grams of magnesium nitrate, that's my starting value. The question is, how many moles of Mg3PO42 will we make? Okay, so if I look at my mole map, I am starting with, I'm going to erase this one and put a new problem up here. So this time I am starting with grams of magnesium nitrate, and I'm trying to find moles of magnesium phosphate. So notice how this time, this problem is only going to take me 2 steps to solve it instead of 3. So we don't always have to use all the steps in the mole map. Sometimes it might just be a 1-step problem, a 2-step problem, or maybe we have to do all 3 steps to solve. This one just looks like a 2-step problem. So my first step is I'm going to use the molar mass. This one can be kind of a pain to add up. You have to add up all the O's and the N's and stuff. But if you add up the molar masses for all your N's and your O's, you end up with 148.3 is your molar mass for the magnesium nitrate. That would get me here. If I mean moles of magnesium nitrate. Then once we know moles of magnesium nitrate, I can use my mole ratio, which remember you find the mole ratio using the coefficients. So I can use my mole ratio to convert from moles of magnesium nitrate to moles of magnesium phosphate. And that's what I'm trying to find. I ran out of room there. Okay. So my balanced chemical equation tells me that for every 1 magnesium phosphate, so remember there's no number written, that's like there's a 1 there, I need 3 magnesium nitrates. So it's a 1-to-3 mole ratio. So when I plug this in my calculator, 112 times 1 divided by 148 times 1 divided by 3, I end up with 0.252 moles being my answer. All right, so I hope that helps, and thanks for watching.